Hello everyone and welcome to my video about the S50, the Seestar S50. My name is Andrew Pearce. Just a bit of background about myself and then a little bit about the presentation. I've been an amateur astronomer for over 45 years and have been heavily involved in a whole variety of observational work over the journey. I live in Perth, Western Australia, so it's a long way from most places, but a wonderful place to do astronomy. So the reason I want to talk to you today about what we can do with the Seestar is, I suppose I have never come across anything like the Seestar in the 45 years that I have been practicing astronomy. It's a fantastic instrument. I know there's also a lot of other smart telescopes which are obviously becoming very, very popular. I purchased the Seestar back in January and have been experimenting with it since. My interest is not really astrophotography. I've never taken an astrophotography photo in my life. I have primarily been involved in visual observing, and that's about it. And recently I've been using some CCDs and remote telescopes to do photometry type work, but have no astrophotography experience whatsoever. And I actually admire astrophotographers. They're a fantastic bunch. They do some unbelievable images. And so I didn't really want to replicate that. What I was looking for was to understand, can we use the Seestar for science? And after my experimentations, I think the answer to that is yes. And so that's what I'd like to go through today. So what I'll be talking about is a little bit about the Seestar, particularly as it relates to how you can do science with it. Some of the useful accessories that I've seen that have come onto the market and I think are very useful to have if you're about to embark on what I have. Then I want to talk about the areas that I have actually experimented with and have produced some fairly good results. And that forms four groups: astrometry, which is precise positioning of asteroids, nova, comets, and everything else; photometry of asteroids, comets, and variable stars; exoplanets, which is interesting; and also asteroid occultations. And then I'll go a little bit about the software. It's important to note that really I think the full benefit of the Seestar is only realized with some extraordinary software that's now available in the market to support it. I think if the software wasn't there, I don't believe the Seestar would be as useful as it's turned out to be. Okay, so a little bit about the Seestar itself, and I'm sure many of you are familiar with it. It's basically a triple chromatic refractor, 3 lenses which correct for color fringing. It's a 50 millimeter aperture with f5, so a focal length of 250 millimeters. The real interesting characteristic of the Seestar and many of these smart telescopes is the ability for it to take short exposures and then store the individual images in FITS and JPEG formats. That's extraordinarily useful because it allows you to use those individual images to do all sorts of things. So that is a key attractive feature of the Seestar and many other smart telescopes. It is on an Altezza mount, which means that it does have difficulty when looking at particularly high in the sky and altitudes above about 75 degrees. Its tracking is not quite as good. So if you're looking at the zenith, you'll really struggle with this scope. But otherwise, obviously, it's a much simpler arrangement to use an Altezza mount rather than a equatorial mount. There's no requirement for polar aligning, all that type of stuff. What it does do is it uses plate solving techniques to work out where it's pointing in the sky. And that's also a very powerful tool and works very well. And to help it along, generally at the start of each session, you calibrate the instrument such that you point it in a number of different directions. It fine-tunes its pointing ability and also provides better tracking, particularly when you're looking at long exposure runs, which is what I focus on. So it is an option in the app on the phone to actually to calibrate the instrument. And I strongly recommend that for every session that you do, that you try and do that. It actually is a very good enabler for a better performance. As you might know, it takes darks automatically and calibrates the images with the darks automatically. So that's all done for you. So that's some of the elements of the S50. Just a little bit more about imaging, which I think is very important, particularly when I'm talking a bit later on about photometry. It has a 2.1 megapixel camera, so it's a 1920 by 1080 image. Really what's important is it has there's a Bayer matrix across the sensor. So you have colored filters applied to each pixel. It is a GRBG Bayer matrix read from the top down. And the good thing about that is knowing that arrangement, there is a number of different software packages around which can be used to extract the individual RGB channels, which is a process called debayering or demosaicing. And that's very important because when we talk photometry, the ability to be able to extract those individual color channels becomes very important. So it's quite easy to do with a Seestar, also with some software. Just in going on with that a little bit, at the top, the diagram you'll see is its spectral response, I suppose, over the various wavelengths for the various colors that you have on the sensor. And you can see the blue, red, and green ones there. You'll notice also that there's a built-in IR cutoff filter, and that's really important. It basically blocks out anything with wavelengths longer than 700 nanometers. That's extremely important because, as you can see, the sensor is quite highly sensitive to those longer wavelengths, and so this actually helps in performing better photometry. Now, what I've done at the bottom is you can see there's a second diagram which shows the standard UV-VRI filters. So photometry tries to use a standard set of filters, particularly the B, V, R, and I filters. They're a standard response. If you buy a Johnson filter, a U or a B or a V or an IR filter from somewhere, and you buy another one from somewhere else, they should give very similar spectral responses. So they're standard filters. As you can see, I've lined up those diagrams to try and correspond, and you can see that there's a reasonable alignment for BVR for the Seestar compared to the Johnson filters. It's not identical. There are differences, but it's a fairly good approximation, although you do have to watch it a little bit, but it's not a bad place to start. So they're important things to note when I talk a little bit later about photometry. Useful accessories. As I mentioned, I've been running the Seestar since January this year, and I have found that there are a number of very, very useful features. And the interesting thing about it, there's a very, very active community for Seestar users throughout the world on Facebook. A number of different groups have sprung up, and there's some very smart people who have actually designed these accessories, and you can 3D print them, so they're available to everyone. They are available for sale, but also what you find is that the 3D printing files are available online, which you can then use to use your local 3D printing shop, so that you don't have to get them posted out to you. And the ones I find extremely useful, the lens cap is very good as well, just to maintain some cleanliness in the lens. The dew and light shield is almost essential, certainly from my backyard, which is heavily light polluted. I don't have as much problem with dew. I have a lot of problem with light, so it's very important as well. In terms of focusing, the Barton-off mask is very efficient and very good. I'm sure most of you are familiar with how that works. The little screen grab at the top shows that it generates a series of spikes, which you then basically have to get symmetrical, and you know you're in focus. And I found it to be a very accurate way of doing it. Having said that, I will note that I've only probably used the Barton-off mask maybe twice since I've had the Seestar, because I find that the focus for this Seestar, once you focus it once, it keeps it really, really good. You don't have to do too much to it, but it is a useful accessory. Other uses, certainly everyone is buying a leveler, which just helps to try and get the Seestar level. It's extremely important to actually get the Seestar level, and not a 2 degrees just so that the circles are green. I think for long exposures over multiple hours, you do need to have the Seestar as level as possible. So I'm saying less than half a degree. I find that makes a difference, and so a leveler just makes it just a convenient way of doing it, and a lot of those are sold online quite cheaply. And last but not least, which I think is what's really enabled me a lot this year, is to have an external charger. It's very important to have a charger to be able to help the Seestar. The Seestar's battery probably only lasts about 4 or 5 hours, and when you have the dew heater on, it's even less than that. A wonderful design has come up where you can see on that picture there that the battery charger is actually held in a holder, which is attached to the unit and rotates to the unit, so the cord doesn't get tangled. It's not external to the unit itself. So that's a fantastic accessory. I find that with a 10,000 milliamp hour external charger, particularly if it charges at 20 watts, That's enough to get through the night, and between that battery and the internal battery, the Seestar, you can easily achieve 11 hours of imaging time without any problem at all. So that's a key enabler if you wish to sort of do long exposures over the whole night. So they're sort of all the useful accessories. As I mentioned, one of the key characteristics of the Seestar is that ability to take short 10-second exposures, and also then being able to use the FITS files that you can download from the instrument for further processing. And that is the key enabler as to how the Seestar works. So what that does is it lends itself to doing what's called time series observations. So that's performing photometry, for example, measuring the brightness of objects over long periods of time. So 2, 3, 4 hours of time. That's where it really starts to be very effective. Okay, so the last thing I want to talk about is about scheduling observations. And there are some fantastic people around that have being able to go into the Seestar itself and develop some additional software over and above the app that's available for your phone. The interesting thing is, must have been about 6 months ago, ZWO released the ability for everyone to understand what their IP address of their individual Seestar was. And so once you can understand what that is, then you can actually have other third-party software to control it. And there's a wonderful group on the Smart Underworld Facebook page, which have developed some fantastic routines that now you can remotely control your Seestar. And the one I use, which is quite a simple one, is called Seestar Run. And it's a Python routine where you can schedule a night's observations. You can put in, and down the bottom there, you can see a bunch of observations that's going to run over the night. You can input the right ascension and declination for exactly those targets, how long you want to run it for, and basically you can just set this up to start with at the start of the night and set and forget it. Really let it go. It does a great job. Obviously, if you clouds or rain, you won't want to leave it alone, but it really is a key enabler. And I've just provided a link there to the GitHub site where you can download some of this software. But some very smart people have done a wonderful job in really helping the whole community, and I've taken advantage of that for the observations that I make. Okay, so firstly, I want to talk about one of the first things I did was to get involved in astrometry. Now, astrometry, for those of you who don't know, is really determining precise positions, particularly for moving objects such as asteroids and comets, such that you can enable the computers to work out the orbits and calculate their orbits. Now, this is precise positioning, so we're talking probably the analog would be establishing the latitude and longitude of a tree in your backyard. So we're talking extremely accurate positioning, and that is then used to calculate orbits. So this is an example of an asteroid that flew past the Earth quite close towards the end of June this year. It came within about 0.75 lunar distances, so about 290,000 kilometres. So it was very close, very well placed in the southern hemisphere, which is good for me. And so I was able to observe the object, 224 MK on the 28th of June, using the Seestar, taking multiple 10-second exposures. And there's a wonderful piece of software that I highly recommend to pretty much everyone, is Tycho Tracker. And I've provided a link there. And that is a fantastic bit of software that allows you to plate solve your images and then stack the images, and also stack them and track them such that they stack on a moving object. So the image you can see there, you'll see right in the middle is just a dot, and that is the asteroid, and you can see the star trails because you're stacking each of the individual images, and there might have been 200 or 300 images. You're stacking those on top, but you're also making sure that the asteroid is the center, and that allows you then to do some very accurate positional measurements of it. At the time of the observation, it was about magnitude 12.5 at the time, and that's in my light polluted skies. I'm probably in a Bortle 6 sky. And so that was quite easy to capture. But the trick is how accurate was your actual astrometry. And what you basically do is you can work out by doing through the software, through Tycho Tracker and another software program called FindOrb, you can input your observations, and then you get an output of your observations, and you see in the bottom right is the residuals. So that's basically the errors of your observations, how much they differ from the sort of the overall mean orbit of the asteroid. And typically what you're aiming for is a residual of around about 1 second or less, and preferably less, preferably half a second or less. Obviously, the lower it is, that means the more accurate your results are. And you can see the ones I've highlighted. They're the observations I made with the Seestar, and they're very low. They're basically, I think the highest is there is 0.67 seconds, but the majority of them, as you can see, are very, very low. So for an asteroid of that type, magnitude 12.5, very, very accurate observations and good enough. And in fact, they were that good that I've been able to actually report those measurements to the Minor Planet Center. So the Minor Planet Center is based in the US. It is the central repository of all minor planet observations and comet observations in terms of astrometry. I went through a process where I had to actually get my observatory, and I say observatory in inverted commas because it is basically my Seestar in my backyard. And I had to go through a process to take a number of different measurements of a number of different asteroids to show that I was getting the required level of accuracy before they issued me an NPC observer code. And my observer code, as you can see on the slide there, is P14. And Netherlands Observatory Perth sounds fairly fancy, but in reality it's my Seestar in my backyard. But clearly it was good enough. My observations have been accepted. And so I've actually done a lot of asteroid astrometry over the last 6 months, and have reported all my observations to the Minor Planet Center. So it is possible to do. I've also done astrometry on comets. They're a bit more difficult. They're not as well defined as asteroids in the sense that they obviously are large and diffuse. They do have a central condensation or a sort of a nucleus that you might be able to target, but they're not quite as it's not quite as good as asteroids. Asteroids are obviously star-like, and so they make it much easier in terms of performing astrometry. But I have also submitted observations to the Minor Planet Center for comets. So again, a very good a way of using the Seestar, and very useful. Just on that asteroid, the next day it flew really close to the Earth, and it was traveling at a ridiculous rate across the sky, and unfortunately the Seestar really couldn't keep up with it, and I don't think any telescope could keep up with it on the day of closest approach. The other way that I have used the Seestar for astrometry is in more transient sort of variable stars. And so I myself undertake a nova search program, and I've been quite successful in discovering or independently discovering about 8 novas so far. And one of the key elements of that, when a galactic nova does have an outburst, is obviously to discover it. The next thing is to try and work out precisely where it is, because it's important to understand whether there was a progenitor or a faint star that was at the position that you knew that was the star that was going into outburst. And so on the last couple of nova, I've actually used the Seestar again to do very precise astrometry, and have then used through Tycho Tracker to come up with a new an accurate position. And then I've looked at and saw where I could actually find a progenitor star. So this is the circular to the right is from the Central Bureau of Astronomical Telegrams, which again is the clearinghouse in the United States for sort of discoveries such as nova discoveries. And this was a nova discovered in Scorpius only earlier in September by Itagaki-san from Japan, and I was able to independently discover it within an hour of him. And then I was straight away able to use Seestar to undertake a precise position of it. And you can see the yellow text is highlighting that is the observation made with the Seestar. And I detected, I again measured the precise position, and from there it was not obvious that there was a real obvious progenitor star at that location, which means the nova has undergone a very, very large amplitude in change in brightness over the time. So again, it's a good tool for that precise astrometry issue as well, again for any transient objects as well, so very useful. And again, I've had my observations reported on these circulars. So that's astrometry. Very useful and certainly something that I'll continue doing. The next thing is photometry, and I just thought I'd spend, for those who are not familiar with photometry, and I'm certainly no expert, I'm learning as I go. It's quite a journey for people to really become proficient and accurate with photometry. But essentially what a photometry is the accurate measurement of brightness. So this is trying to measure accurately the brightness of all sorts of objects, not necessarily just stars and variable stars, but also comets and asteroids. So they all follow pretty much the same process. You can use different filters, and this is why I was talking earlier about those standard Johnson, BVR, and I filters. You can certainly use different filters, and the interesting thing about those is when you do photometry with those different filters, that provides you information on the star's colour, which is also quite useful. So what we do is we typically perform what's called differential aperture photometry, and when I say aperture, I mean that essentially this software you use will place an aperture, as you can see on the right top of the screen there, will be placed around the star image, and it measures the pixel values within that aperture. There is also an outer annulus that's used, and that measures the sky brightness, and that's subtracted from the aperture pixel values to give you the true value, and that's converted to a magnitude. So that's the process. You typically also then compare a target brightness with stars of known brightness to estimate a magnitude. And there's, again, a number of software packages that will actually identify the variable star for you and some comparison stars, as you can see in the bottom right. And then that will perform differential photometry and come up with an actual value for your variable star or your comet or your asteroid. Is very much the same. As I mentioned, the Seestar's RGB channels, they sort of approximate the standard filters, give or take. Sometimes there's some variability due to particularly stars' different colors and whether they have emission lines and everything else. There is some variability there. But again, there's a number of different software packages that can actually extract the various channels, so you can actually do that photometry. So that's what it is. And then what I've got is some examples of what I've been performing photometry on. First time was a bit of an effort here. I tried to do a photometry of an asteroid, and the idea of that is to try and understand whether you can measure the rotation period of the asteroid. I picked the asteroid 43 Ariadne and was able to do multiple night run in June this year, and looked at the phase diagram to understand whether I could pick up a rotational period. I use the Tycho tracker software because not only does it do astrometry, it also does photometry as well, which makes it very, very useful. It was quite a difficult observation, and the reason at the time was because the amplitude of the asteroid was less than 0.2 of a magnitude. It was probably closer to 0.1 of a magnitude, and that makes it difficult for the Seestar. That's getting a little bit on its limits. But I tried to fit a curve through the you can see there's a bunch of noise there associated with the photometry measurements over those various nights. But the scale on the left-hand side, that's between 9.4 and 9.6 magnitude. So it's only a 0.2 magnitude variation. So it's been pretty tough on the Seestar, to be honest. But it looks, I did some work with the Tycho tracker, and I worked out a period of about 5.78 hours. Interestingly, I picked up was that the published period for that asteroid is 5.76 hours. So I actually managed to get quite close, but I must admit I'm surprised at how close I got. Unfortunately, well, the reason why is that I picked that asteroid is that I was led to believe that it had an amplitude of about 0.6 magnitudes, which would have made it a bit easier for the Seestar. But what I didn't know was that the amplitude of the asteroid, because of how it rotates, it is actually different depending on where it is in its orbit. And you can see on the bottom right there, it sort of varies sinusoidally between 0.1 and 0.6 of a magnitude amplitude. Unfortunately, at the time my observation, the amplitude was about 0.1, so it wasn't too good. If I'd waited a few more months, we would have seen a much larger amplitude. There's a very good source for asteroid light curves, which is the bottom there, the asteroid light curve database, which I've provided a reference for it there. In terms of useful scientifically, look, I think for amateurs, probably the majority of asteroids that do rotate have had the ones that have been measured pretty much have been measured. So I'm not too sure there's a lot of scope for amateurs there, but it was just a useful exercise to go through, and shows that the Seestar has the ability, even though it was quite a difficult target. The next one is comets, and I've also done photometry of comets. So just firstly, the Seestar, there's a picture there of Pons Brooks, 12P Pons Brooks, which is a bright comet that was around this year. This is a 12-minute exposure on the 15th of May that was taken. So as I mentioned, 10-second exposures. The issue with comets is they move, of course, and they move quite quickly. So Pons Brooks at this time was moving at about 2 arc seconds per minute across the sky. The Seestar's resolution is about 2.3 seconds per pixel. So really what it was saying that over a 12-minute exposure, it was going to move over multiple pixels. And so you don't want to smear the image. For photometry, you want to make sure that the comet appears stationary and that you stack the images such that the stars are trailed, and that's what I've done there. I use another wonderful software package called Astro 8, and there's a link there which is very good at pre-processing images such that you can track and stack on comets, and that's the resulting image. I have no experience whatsoever in some of the various image processing techniques, and I'm sure that people could get my images and make them look a hell of a lot better, but that's not really my goal. My goal is to get the science out of them. But really, the photometry of comets is exactly the same as for stars. It's just that you have to make sure that your aperture captures the whole coma. So what we're looking at for photometry of comets is to measure the coma of the comet, which is basically its head. We need to measure, that's the brightness. We don't want to measure the brightness of the tail. It's the measurement of the head is what we're looking for. So this is how we do it. Again, there's various software packages out there can do it. I use a package called Copra, or KOPR, and again, there's a link there as well, which I find a very, very useful tool. And there's a picture, the same image. What I have done though is I've extracted just the green channel, so it's basically almost a visual or V type of image there. You can see there's an aperture around the comet's head. That's what I'm measuring inside that aperture there. You can see the stars have actually also been identified. The yellow ones are the ones that are pretty much my sun-like, so they're the best ones to use for photometry. And as you can also do things like measure the tail as well. And so using this bit of software, we're able to then get an integrated magnitude for the whole comet, which is called M1, or total magnitude. So that's the software. What we do with the observations, there is a number of different places around that will actually take the observations and use them. Essentially what you end up doing is all the observations worldwide are brought together. They're plotted on a light curve. So this is a drawing which shows magnitude on the left-hand side and its time over the bottom. And there's the brightness of Pons Brooks as it comes close to the sun and heads off down again. And you fit a curve through it, which is that red line there, and you then get an equation for that curve, which gives you characteristics of the comet itself. So the value of 5 is its absolute magnitude. So that's the brightness the comet will be at both 1 AU from the Earth and the Sun. And that's a good characteristic to let you know when you can compare comets. Sometimes they're intrinsically bright. That's quite bright for a comet. So Pons Brooks is quite a bright comet compared to others which might be much fainter. And then the 6 at the end, the log R, that gives you an indication about how rapidly it brightens as it varies its position with respect to the sun. So some comets brighten very rapidly, others a lot slower. And again, by measuring that, it gives you some indication about some of the characteristics of the comet as well. Now, my observations are there amongst the hundreds and hundreds of there. They're difficult to see, unfortunately, but they're generally on the right-hand side of the graph after that purple line, which is perihelion date. They're some of the black dots, not green dots. You can see they're generally a bit fainter than visual, which is not unusual for a CCD. But I've contributed quite a number of observations with the Seestar for this light curve. So all the observations are sent to the Comet Observation Database, or it's called COBS, and there's the link there, as well as the International Comet Quarterly. They're the two main international organisations that accept all observations from comets. And as I mentioned, they're the way we can plot the curves to understand some of the characteristics of the comet itself. And that's happened for a lot of, and most comets happen that way. So that's comets. Then we get into variable stars. And of course, photometry, there's a lot you can do in the variable star space. As I mentioned, I like just the ability to let the Seestar run for hours and hours and just by itself just gathering data. And so stars that actually vary in brightness over a period of a time scale of 2 or 3 hours are ideal for the Seestar. And so it's a fantastic instrument that you can just leave and the next morning download the data, analyze it, and you can come up with some wonderful results. So on this page here, what I'm showing is what's a couple of different types of stars: the Delta Scuti and SX Phoenix stars. They're pulsating stars. They've got periods less than 0.3 of a day, so short pulsators, and they're quite regular. And as you can see, the top one there is CY Aquarii. That is an SX Phoenix star, and that has a period of about 80 minutes. And you can see a wonderful series there, which shows the star brightening. It's got an amplitude of around 0.8 of a magnitude, between about 10.4 and 11.2. And over a period of about 5 hours, I was able to see three peaks, as you can see there. So that was good. And down the bottom there is a Delta Scuti star, which has got a period a bit longer than that. But again, you can see that rapid rise up to a maximum, a slower decline and rapid again. That's for the star EH Libra, and that's over a period of about 3.5 hours as well. So what we're looking for over long time periods is if we go back and observe these stars over a number of times over a longer time frame, it might show some changes in the period of those pulsations, and that's important to understand. So it's worthwhile keeping an eye on these, and they're good fun because they're good large amplitudes, and they vary quite quickly over a time scale. All my observations for variable stars are submitted to the American Association of Variable Star Observers, or the AAVSO. They're a wonderful organisation, lots of resources to help observers. They provide guidance, software, all sorts of things. The star charts themselves, everything you need to study variable stars, so I highly recommend them. That's one class of variable star. The other class of variable star is eclipsing binaries, and these are obviously double stars, or stars revolving around each other. And what actually happens is that one star passes in front of the other and eclipses it over quite regular time frames. And as you can see in that diagram there, it travels around, and then when you see the main eclipse is when the fainter star is eclipsing the brighter star. And so what you see there is a series of different stars that I followed over the last few months, which show again a time frame of around about 2 to 3 to 4 hours. You can see actually that there's a definite dip to those, or showing the eclipses. Generally the primary eclipse is what it's showing, and you can see that I'm picking up them quite well. Now, some would say that the accuracy is not the best. Yep, that's probably fair, although I believe that, again, I think it's important to do a number of these and then measure them precisely to try and determine the period. You can see the middle one there on the right hand side, AQ Tucani is the name of the star. It's a southern star. You can see that's got a flat bottom on it, and that obviously means what's happened there is that the eclipsing star is quite big, and it's probably bigger than the primary star, and so it's taking its time to get across the face of the primary star, and so that's why it's sort of bottomed out as a minimum. But again, these have got typically amplitudes of about 0.3 to 0.6 of a magnitude, so fairly small. But again, the Seestar does a great job in detecting those. So the intent of those, again, the same thing, is that by going back to these regularly, we might be able to detect some kind of change in the period, which is important to understand as well. Okay, almost there. The last one I want to talk about, a couple of things I want to talk about, and the next one is exoplanets. Now this is, I would say, a little bit controversial, but I'm happy to sort of share my experience with it. I take an example of an exoplanet. It is a planet rotating around the star, which is titled TOI 4463A, which is actually an 11th magnitude star. It's in the constellation of Hercules. This is a plot from NASA, which has a database on these exoplanets. It's about 565 light years from the Earth, and this planet rotates around the star with a period of about 110 minutes, so it's quite close to the star itself. The sort of the grey donut around the star is what we call the Goldilocks zone. So that's the habitable zone. So if we were to see a planet in that space, then it might be similar to having the characteristics of Earth, and so that might be another Earth where you could see life. But unfortunately, in this case, the planet is very close to the star, so there's probably next to no chance of being habitable. So not that one. But it was intriguing to see whether the Seestar could detect an exoplanet transit, and so I thought I'd give it a go. I had no preconceived ideas that I'd actually be successful, so I just thought I'd give it a go. So this is what I came up with, and this is the observations I made. Essentially, it's hard to tell. Certainly, I used analysis package that is from the Exoplanet Transit Database website, which the link is there, which actually analyzes the observations to detect a transit. And there's a fair bit of scatter on the observations, as you can see, but the software is actually picking up a dip. And what it's picking up is it is showing a total duration of about 110 minutes, which is about what is published, the value is. So it looks about right. It's also happened about the same time. So those two drawings, figures at the bottom left are showing my observations, the blue dot, and it's basically showing that I potentially am picking up a transit because it's showing the duration is about 110 minutes and it was occurring at about the time that it was predicted to occur. So you could say, yes, I have picked up an exoplanet transit. I just a little bit wary about it because simply the scatter of the Seestar is such that, yeah, it's be difficult to really be very confident that that's what you've done. But I've given it a go. I don't know if I could do too many more. Lastly, I just want to talk about an asteroid occultation as well. Now, this is not me, but I'm super impressed with what this guy did. He was an amateur in New Zealand, and he has actually used the Seestar in the lunar mode to actually record an asteroid occultation. You can see on the diagram to the right there, the light blue trace is actually the asteroid occultation. I understand it was about 15 seconds as well. He used a software package called Tangra to process the video images. Details are on Facebook. It's a fantastic observation. I'm very impressed that you could use the Seestar for that. I haven't tried it myself, but it might be one of those things I will try. So that brings me to the conclusion of the bits of science that you can do. I'm super impressed with this performance for a very cheap telescope. In terms of cost-wise, it's amazing what it can do for what it is. But again, I probably want to reiterate that I believe that it's only as good as the software that is used with it to try and extract the maximum usefulness from it. I think that some of the software is a key enabler for the Seestar. And look, this is not an exhaustive or exclusive list. The software I use, I certainly recommend Tycho Tracker, AstroArt, COPRA or KOPR for comet photometry, and the Seestar Run to schedule the observations. But there's multiple other software packages out there that can do similar things. But I think that's the trick, is you do need to get very good software to work with it. But I hope that's been useful, and I hope that sort of generates some interest and possibly someone to dip their toe into doing some science with Seestar. Thanks very much.